But they then typically announce instead of but they're all coming with the microphone as well.
But then I can see from here, from what you showed me, say that x is the least upper bound if for every other upper bound we have any other upper bound, we have that y is above x. Then x is said to be the least upper bound or supreme. The important thing to note here is that suprema, if they exist, are unique. We can do the same thing for lower bound. Okay, there is no guarantee that the other bounds are not necessarily unique. However, we have at least upper bound, then it is really upper bound. And the same for lower bounds. However, the story for maxima and minima. Okay. We take again the set x for partial ordering and the A along the subset. The element little a is said to be a maximal element. If we have that each x in A that is beyond, it implies that x equals A. Okay. So we have an element. It's a maximal element of A. If there's something in A that exceeds it, then that element x that exceeds it has to be equal to A. Now, let's add to this collection of terms the concept of largest element. So, if an element little a that is above every x in A. Okay? So it is an upper bound of A from A. Then the A is the largest element. The largest element. It is unique. So if we have the set A is the then it is also a maximal element and it's the only maximal element. And the bad news is maximal elements that exist any longer. Okay, let's take our two component-wise ordering and give you the set A here, which is 2 points.
It's the previous slide, your definition of moments.
It's if A is the largest element, it's also an upper bound. So it's an upper bound for your set.
Okay, something else.
It's upper bound for your set and it is in A.
I suppose the supremum doesn't need to be.
Your supremum doesn't need to be A. Your maximal element may not be comparable with every element. The only thing you require is for maximal element that if you exceed it, then you're equal to. Okay, so it's very, very simple. Two.
Back.
Set A, we're looking onto component-wise ordering, and we've got the two element set. It's 1, 0, and 0. Both of these elements are maximal elements of that set. If we have a point x1, x2 from A that exceeds 1, 0, then it has to be equal to 1, 0. So 1, 0 maximal element. And similarly for 0, 1. But neither 1, 0 nor 0, 1 is an upper bound of that. Neither of them is the largest element. Okay, let's continue with this. And if we look for the supremum of that set, the smallest upper bound of this set from R2 is 1. 1, 1 is not an X. It is an upper bound. And if you take anything in R2 that is an upper bound, beyond it, then if you take any upper bound of the set, then it is beyond. Let's see that x1, x2 is an upper bound of A, then 1, 0 has to be below x1, x2, and 0, 1 has to be below x1, x2. So x1 has to be bigger than x1, and x2 has to be 1, so x1, x2 is below. That's okay, so that is dealt with those basic concepts that we need from. We now introduce the next step in our structure. We're looking at all the vector space. Then we're only looking at the reals. Then you can do complexified versions of them, but it takes not a very nice structure. We will deal with the real vector space. So we have E vector space of the reals, and we also assume that E is partially ordered. We say that E is an ordered vector space if we partial ordering structure have the following compatibility conditions. So if x is below y, then x plus z is below y. Something is
Looking now.
Is someone with the risk connection? Not very anymore. Okay, we have the two compatibility conditions that this is your additive compatibility condition. If x is below y, then x plus z is below y plus z. And a multiplicative compatibility condition that if we have a real number alpha, it is non-negative, then and x is below y, then alpha times x is below alpha. So the algebraic structure and the order structure need to be compatible. And we say that the element x in E is positive. There are two conflicting terminologies here. Positive or non-negative, if x is above 0.
Are we saying that x 0 portion of x is strictly or is
it's not strictly. This ordering here, if you look at this, because you just take the simple condition of equals 0. And we see immediately that it's not a strict order. It's not a strict inequality. So your positive elements include 0. And so there are two terms used here, positive in some of the literature and non-negative in other parts of the literature. Most of the slide uses the term positive. Operated theoretically in the area uses the term positive, and the more algebraic people use the word in terms non-negative, but then it is equivalent. Okay, second positive. There's one.
Oh.
It's about it.
Make it swap.
Sorry?
I'll do it.
What books are there? Yeah, maybe.
Yeah, it's sitting into.
No, that's. Ah, that's like us. Okay, now let's share it. Okay. That's fine. That, okay. I think we're in business again. Yeah. Examples of ordered vector spaces. We have the real with less than or equal to. Again, our regular component line ordering, our graphic ordering. The continuous function on some topological space omega, new dynamic function, plane-wise ordering.
Okay.
And point-wise addition, etc. That is an ordered vector space. And lastly, one of the more interesting ones, and ones that relate to us, is LP, with almost everywhere point-wise order. So, if we remember, LP consists of equivalence classes, so then we have almost everywhere point-wise. Disappearing. Okay. Now, we say that a partially ordered set X is a lattice if each pair of elements in the set have a screener. So examples of lattices, again, we're dealing with the power set, that is a lattice, and if we have two subsets A and B of X, then the supreme number of A and B is just the union. The infinite number of A and B is just the intersection. And one can go through the technical details to show that both are included. But both are indeed the supreme number of B. Okay, another example. If we have some say, omega, and we look at all the maps from omega to the power set of some set x, that is also a lattice with the partial ordering given by set f is below the set g if f of omega is below g of omega for each omega and capital. So it's a pointwise ordering. Partial ordering is induced by partial ordering of the parts. And again, that lattice because we take a pointwise suprema and pointwise. So that's a more obscure example here. Some that are closer to home, the real value continues real value functions of the interval with pointwise ordering. An example that doesn't work. C1 on subinterval. It's not a lattice of a pointwise operation. Take a very simple example. You take the function x equals x. That's the C1 function. You take this and you take the constant zero function, and now you're supposed to be able to take the supreme number and an integral of those. Well, certainly the set is bounded. There's a bound from the set in actual fact to the but there's no least of a bound because every time you try to find a bound for these two functions, which is C1, so that fails. And it's a simple example of a lattice. 4-element set contains pointwise ordering 0, 0, 0, 1, 2, 0, and 2, 1. And if you check it out, you'll see that that is a lattice. Very simple. You know, that doesn't have to be this. Yes.
The previous value construct the lattice. Why did you choose the disjoint on
You can check that what is the what you obtain between the supreme.
Yeah.
Your supreme has to be an upper bound for you A and B. So this is containing, it has to contain A. Okay, various versions of in that we mentioned because okay, let's start with the particle with set x. Set x is order complete if every non-empty subset is an infinite. Oh, that's not going to work very well. That's when we have very large sets. In general, that's going to create a problem with us. We usually going to have dedicated component. That's it. It's a dedicated component. Every non-empty subset that is bounded about it is supreme. So this is certainly stronger than For it to be a lattice, we only need each set of two elements. Each two-element set has to have a supreme. Okay, so there is incompleteness is a very nice property, and we have it in the reals. In fact, your LP states of that can complete with a pointwise ordering. So they all have a very nice structure. There's one exist there to be sigma data incomplete. Every non-countable subset of X that is bounded by the supreme. That structure is nice because it enables you to work with sequences rather than more complicated types of convergence. But often in lattice theory, you want more convergence than just sequence. Just requiring sequences to converge is not always adequate. Okay. And the last is the narrative. Okay. Now we come to what is called a Riesz. That is R has a partial ordering on it equal to partial ordering is compatible with the algebraic structure and can get into an ordered vector space. Okay, and it has to be a lattice with respect to that. So we have the partial ordering which induces the lattice structure, we have an algebraic vector space structure, and compatibility. Once you have those, you have what's called Riesz. Examples of Riesz spaces and quite abundant in analysis. The reals are in the compatibilized ordering, are in the flexible graphic ordering. That one's still in there. CX, where the continuous function over some topological space. X, the LP spaces with A equivalence classes. The set of real value maps set X. We set X mapped from X into R under pointwise ordering. Maps just pointwise. With superior to pointwise. Briefly. Okay. One of the things we need in a Riesz space is to look at the positive elements. And they form what are called a CoE. Why? Okay. A CoE is a subset of your Riesz space. If we can add elements in that set and end up back in the set, we think of a wedge. You add two elements in the wedge, we have to end up back in there. We take any element in that set, we have to be able to multiply it by any non-negative real number and end up back. So you can continue out on brains from where you start. And lastly, the last kind is that if you have an element in your CoE, and the negative of that element is also in the CoE, the only way you can have that is if you are at 0 at the base of your CoE. So your CoE is based at the origin. Otherwise, if you remove that last condition, you have what's called a wedge. Okay, in particular, the non-negative elements in your for the positive cone of E, and knowing that cone is equivalent to knowing your partial order. So we have that F is below less than equal to G if and only if F minus G is in your positive. And some of the nice properties we have, which those of you who, sorry? I have that in the case of the power things in the off. The black cable in one step. Okay, so we have that in a Riesz space, we can form people have done measure theory. One of the things you do in measure theory is you take a function and you decompose it into its positive and negative parts. Important, because when you actually work with it in measure theory, you work with the positive and negative parts, because the positive and negative parts are both non-negative, aren't they? So you can work with non-negative parts. So, Riesz spaces have enough structure to do that. So if we take an element in our Riesz space, we can form the positive part of it, which is the supremum of 0 and the element, the negative part of it, which is the supremum of 0 and minus. And we retain the same composition that F is the positive part of F minus the negative part of F. This gives you that your whole space is made up of positive components. It's different to the positive elements. And absolute value of the elements, which is the supremum of F minus F, and that is equal to the positive part of F, negative part of F. And there's this last interesting identity that F plus G is just the supremum of F and G plus the infinite. So this decomposition enables you to do a whole lot of work with positive elements, just the same way you do in measure. Okay. So far we've built a whole lot of structure. And okay. We now want to look at various subspaces, Riesz spaces. And the first of these, there will be two particular types of spaces. One is a Riesz subspace, and the other one is like the last one will be a back. Okay, so we have a Riesz space, and we take the vector subspace F. It's called a Riesz subspace. E is closed under the operations of supremum and infimum, thereby supremum and infimum computed in E, not computed in F. So to be subspace that's closed under supremum and pairwise supremum and infimum, but the note that this has to be computed in E. Because we can have the case that you can compute the supremum and infimum in F, and then that's the same as the supremum and infimum. So you need to be able to have the supremum and G computed in E is again F, and in which case we will get automatically the supremum of F and G as computed. Okay, so that makes you say that the subset is solid. If whenever we take an element of the set, let's call that element G, and we look at all the elements of our space, E, that have absolute value less than or equal to the absolute value of G, so we take all the elements F, E, then they are automatically in our set. Just think of a characteristic function. Let's say the continuous functions are the interval minus 1. You look at all of the functions that are 0 for x for your part of the interval minus 1 to 0. That is a solid space. Okay. Okay. A vector subspace that is also solid is called an ideal. It's called an ideal. And an ideal of E is a special case of the Riesz. Some examples. If you have a finite measure space, then an infinity is an ideal of O1. And the continuous functions on omega, the Riesz subspace of the maps from you open the kind of door, everything is. I think it's this cable. I don't think it's. I don't think it's.
You moved that cable just now, then it was fine. When you moved that cable,
Will we come back again?
it was fine for one.
Sure that it's HDMI cable. It's problematic, not the power cable. Let's do next slide.
Professor, what's this definition?
Okay.
Just let's wait for the English definition.
Okay, the continuous function. Same thing. Control H. You see. Oh, we have progress again.
Can you just kind of put it on the slide?
The next one.
Oh, no, thank you. Okay. And the last point here, which we will have time to get to, is that continuous functions of omega is a Riesz subspace. You can form superhuman in there. And say it's like that, but it's not an ideal because it's not solid. Not an ideal of because if I give you the one function on omega, that's certainly continuous. I can give you something that is around, it's one part of characteristic function of some subset of omega, which is omega. And so empty that there will not be omega if omega is cleared. Okay. So say in E is an ideal if and only if for the two conditions satisfied, if is a subspace in E, if F is little f is in capital F, there if and only if its absolute value is also. And each G in the positive cone of E, we have that G in H is equal to F for each non-negative H. So those are another set of conditions which give you containment in your. So that's an ideal. The problem with an ideal is it lacks degree of order closedness. And how do we build that when we haven't got a notion of convergence? Okay, so that's what we deal with now. And so we want to look at a special type of ideal. So we have reset E, E, and we're going to require the and if each subset B of F, the existence of the supremum of D in E, looking at it with respect to being a subset of E, if that exists, then that supremum is a gain of F. Okay. So that is, if you take supremum in E of elements of F, that again has to live inside this. Okay, in which case we will get for free that is supremum of E. That's the fundamental. Some examples. Counterexamples. We have a finite pressure space. Then infinity was an ideal. But it's not a bad. And you should all know from measure theory, how do you approximate your measurable functions when you want to do integration? You do a type of stepwise approximation from below. You're looking at non-negative measurable functions, you approximate it from below by multiples of characteristic functions, linear combination of multiple characteristic functions. Those approximations are all in our infinity. And they approximate the positive part of any L1 function. So, you can get to every element of L1, every non-negative element of L1, and supremum of the subset of L infinity. So, if you try to do the supremum here, you can form a set of all of those and get all of them. So, it's clear that L infinity is not. Okay. Already, the component parts order, and you enforce various components of your some fixed collection of components to be zero, then that is a band. And in fact, every band in R deal with in terms of that characterizes.
And I'm looking for integration. So starting with all the derivative
well, the code is it's a closed subspace. It's closed under addition and multiplication by non-negative state. You don't have you take the active inverse. In general, you often get variables generating.
So if none of us
Yes. Once you start doing equationing, what you're going to find is that ideals are not good. Because we're going to get to something you are Archimedean property. We'll get to in a few moments. It's part of the Riesz Archimedean property, and the equations are ideal. We can't guarantee our equation space. So, if you want to guarantee that your resulting space are Archimedean, you have to work with that. And the problem is, if you don't have Archimedean, then you don't have uniqueness limits. But that's a little bit of where we go. So we now, let's say we've done the algebraic side of things. But as you saw when we started to talk about a band versus an ideal, we're already closing sets under the prima. So somehow there is already a sort of analysis going on there. You are looking at putting your prima subsets, taking the big space that has to live in the small space. So you're doing a type of closure operation. You get from the ideal to that. We don't have stability. And what we now are going to look at is what's called Naismith convergence. Convergence of nets. Nets are generalizations of sequences. Sequences, your index sets are the natural numbers. But believe it or not, you already in undergraduate, you already played with more general objects than index sets of the natural, didn't you? Because some of the limits of the reals. Yeah? it so happened that there's such a nice structure that it really didn't matter whether you work with sequences or not in that case. But as soon as you start dealing with fixed bases, you can't get away. So let's look at what is a feasible index. Feasible index sets are called the directed set. Okay, the directed set is a non-empty set. It's equipped with a relation, and that relation is not necessarily a partial. It has reflexivity, it has transitivity. So alpha is below alpha. If alpha is below beta, beta is below gamma, then alpha is below gamma. It has an upper bound property. And that is, I give you two elements of the index, alpha and beta, there has to be a successor somewhere in the index. Something that is above both of those. Doesn't have to be at least upper bound, it doesn't have to be a direct. It just has to be an element. So if I give you two indices, alpha and beta, there has to be another index somewhere above it. That gives you what is required. Okay. We can use power sets for the index set, actual properties. If you look at the set 0, 1, 1, 0, bring its another directed set. Two elements with no success. If we look at set 0, 1, 1, 0, and 1, 2, that is the directed set. We can check that. Okay. Next, this is Morse convergence. If we take a research E, be a directed set, and we have a family of elements in E indexed by D, that is what is that's for the net. So the family of elements in V space indexed by directed set. But the question is, what do we mean? What use is that? Generalization of the sequence. Okay, let's start off by looking at some simple cases and increasing it. So if we have a comparison rule for the indices, so alpha is for the beta, then we need for it to be an increasing end. And we do not and if we have such a net and it has a supremum in E, then we write that. And as we will see, this forms the basis of convergence. This is not a topological convergence. You've spent your lives dealing with topological convergence. This convergence is not topological. Okay. And we can do the same thing for the increasing end. We just change that. Okay. So we can okay. The next property we really do need of a Riesz space is the Archimedean property. Why I'm saying it here is because we get an image with money. So if for our Riesz space to be Archimedean, we mean that if we take an element from the top of the kernel, which we have 1 at the end times f, then influence of that sequence, it's a net indexed by the natural. This is a special case of what we talked about. In this case, we only need to use then that influence to 0. You can build resources which are not Archimedean. It is not arbitrary. Throw away. It's not, doesn't, you don't get this form. And we need Archimedeans because otherwise your coordinates will not be. What we do know is if our least space is very incomplete, you get Archimedean field. And we now get to the point where we can talk about ordinals. Okay, we have the net index like knee. We say that the net alpha converges to so if there is a net G over some index set, which is decreasing at a infinite 0, and each element G each index set, there you can find an element of your original index set for your net, so that all indices beyond beta, we have the difference, absolute value of the difference in F is below G. Okay, so these, if you think about your epsilon delta definition, these are your epsilons. But now you have an increasing family of epsilon. These, if you're looking at how close do you have to hold, looking at, let's say, sequence 1, this would be how far out of the sequence you need to go. How far out in your original index of your net do you need to go to be below that? Okay. So that is the notion of convergence. It's called Witwatersrand convergence, very good nets. It is not, in general, topological convergence, it is called order convergence. And if you look at all the things that happen in measure theory, you have many different types of convergence in measure. You have pointwise convergence, you have some sorts of norm convergence, you have convergence in probability or convergence in measure, and I think that now you have. And they all interact. Okay. The good news is that if you are dealing with a dedicated complete free space, you don't have to fiddle around with two different indexes. You can use the index set for your epsilons to be the same as your original index set for your net. If you don't have the incompleteness, so the good news is that if you're working in a dedicated complete free space, you only need to use one index set for your net. You get free the Archimedean. Okay. And another nice thing you get is that if we have an upwards directed net with supreme, then F output is convergent. I said it's a template that supreme, working with the supreme is a template for your convergence. So that if you have a negative downwards directed, then it's convergent. And one or two things that we have an Archimedean space. We say that step S is ordered around each net in S, order limit F in E has the F is back. Just same like you did for sequential closure. But now with respect to this. And the bands are exactly the auto-closed items.
Question. Is the assume what is the limited level field?
What do you mean? Are you're treating, you have to be careful. Look at sequence can be viewed as a map from the macros into your space. Similarly, the next can be viewed as a map from D, your index set, into your space. Okay, does that answer the question? But often, in a read space, often you'll have read space functions. So you have many different things. And now, one of the one nice things to just noting, I like reading. Sorry?
No, no, this is because we want nothing that's perfect. Master student can follow, if your master student can follow, we do. Correct, just that we have time until 1 o'clock. Lunch can serve.
Okay, when do you want to stop at this point?
No, I finished.
Okay. Because we will, after this topic, we will finish all the research preliminaries to set research. Yes.
No, let's finish now, we know it's done.
Okay. I have one or two things that you can, if you look at, go through this quickly, we're looking at your argument research, and we form a set of objects that are bounded by multiple objects. So we look at all the elements G and E, whose absolute value is less than equal to lambda times F, and we let lambda vary through all non-negative reals. Then this object here is an ideal. Very special ideal is called the ideal generated. An ideal is generated by single elements called principal. If there is an element in our research, so that the entire research is generated, is the ideal generated by the then that element is said to be an order unit generated from space. The ideal builds generated. Okay, some examples. L1, the cosmic one function in L infinity is an order. And we can look at CX, CK, where K is a compact set. This is in fact a Dedekind complete restate, and the cosmic one function. And in fact, every Dedekind complete Archimedean restate all units can be represented as a CK space called Stonian spaces, where you have extremely disconnected sets. Anyway, that's the representation theorem. And we can do the same thing for back. So now we have to have a limit. So we look at all the elements G, E that can be written so that the absolute value of G in F, and we take the supremum of that, that's just the absolute value of G. The second value is a band, it's called band generated by F, and still band. And if there's an element E, so that the band generated by E is then called E. And that if L1, then you where you use the finite measure, the constant one function, when I can affect any constant positive function, the constant function for positive constant is the equal unit. And then many other equal units, those are not just and if L1 mu is an infinite dimensional, in other words, it's not R, then it does not have multiple units.
Did we define a finite measure?
Sorry?
Did we define a finite measure in this context?
Just the measure of R. This means the measure of your whole space. U of omega. Lately, it should be L1 omega A mu. So it's measure space. So mu of omega must be probability space, and there are examples of that because the measure of the whole space is you can extend it to sigma finite as well, and you can also even if it's sigma. The finite dimensional one, if finite dimensional L1 reduces to Rn, size of R. You then need components. And well,
My question from the audience. One. What is the short form? Why is it changing?
the first thing is that it's not because we're throwing out logical convergence. It is that if you want convergence, naturally we have no presumed topology. Okay. We have a presumed order. Partial order. But we think we only have anything to it. Okay. And if you say, well, okay, I'm going to define my place, it's not a place. If we're going to define one, it's not an order. And then they're going to be closed into complements. Good well. So now you've got a topology. But now, let's go back to our concept of consent, and we've got a net convergence in our order sense. But now we look at it in terms of open set convergence. The two are not compatible. You don't automatically get it as an added assumption. And then you get what's called a topological risk. Yeah. It's not critical in what we do. But depending on what you're building, actually you need. Okay.
In the case what is the intuition?
Well, what you find is that when you start working together with your the movement between order convergence in measure and things like that works far more cleanly. The connection between the different, if I there is a very good the connection with the other convergences. Okay.
Are there any further questions?
So, research is learning this thing.
Yeah.
So, what was the impetus?
Well, we were actually interested in statistics, but we functional. And so, what is we wanted a good, solid mathematic routine structure. And if you actually look at the stochastic probability literature, it is a large amount of exception with very little attention to detail as to what are the real assumptions for the making things. So we started analyzing. We spent a couple of years before we wrote anything. And setting up a structure which abstract structure, which is faithful. In other words, if I restrict my life to L1 over a probability measure, I get back very close to what from obvious to gathered process. Yes, we are more general. But we can immediately relate to what happens for measured heritage. We do get fundamentally new, more general results, but they are interpretable in terms of measured theory and probability. So we wanted a structure which was good enough to take our results from abstract back to the world where statisticians and finance people and stochastic people. But it's stronger and more general.
I think that is enough for this session. Apologies for the technical problem, but we really sorted them out. In this world is perfect. Starting from the next session onwards, as you can see, we ironed out all the problems. There won't be any more technical problems. So we wish you welcome you back to the afternoon session after a short lunch at 2 o'clock. And then tomorrow we'll have a final session. Watson, give us some time. Okay, thank you very much.
Well, it's not when you look at everything that you know, you see what I mean.
Also,
In some sense, it is. So it might not be really nice. Well, the trick is the next bit. Devil's in the details. All the research about that, painted, all of a sudden you take the research, and you're restricting it to yes. And it's not waiting to do the same thing.
no.
The restriction of the map is not the same again. But it could be done.
So that's why I
But technically, it looks identical. Each one of them maps to bound,
yes.
but there's hidden stuff. Putting the restrictions in it, I don't know. Then you start seeing that the actual thing in working on the same. When you do a restriction, you're actually moving into different space. And that's where you're taking something from the same object. But restriction, things like that, they're not part of it. Even though they're simple numbers, are
It's so easy when you just look at that symbol.
and it's your simple math. The reason it is obviously not. I saw that in between those we actually university other one there's actually a distribution operation which we constant. And that's where the problem actually
Implicitly implied.
but technically you take this function change or they could have function when you compute it, you can say that, but it's not acting on differences. You're not acting on differences. But if you take it from the original object to where you ended up,
Yes. Maybe this would be our explain the Trinity.
Otherwise, I can see you, I have the e-versions of the foundational paper. They're very, very careful. And you know, when you do some of these things, it looks, you get this rocket operator. And it tends to look like zero in some of the entries, but they're not zero. It's literally the operator takes the value of zero, but it has a very specific domain. That's not just the zero operator, it's zero operator. It is not. And it's just the domain of that operator. The value that it's zero is irrelevant. It's a massive constraint on your domain. Because that operator is the dual of another operator, which is a very big domain. And super big domain, and now this thing that looks like zero actually. That's what your constraint is between the domain. Not
Must develop a better way of showing domain separation.
yeah, the domain is critical. That's why I did the duration. The restriction. It's not, there is a missing step in it. But that restriction is actually, the restriction often usually is true. They found that even like the restriction, you can't apply it to you can't apply the inverse reason. It means you have to but that restriction actually means against yeah. Always lost in the video.
I'll read it again. I'll read it again. Why didn't you tell us? Oh, we're starting at really. Okay. Okay. Okay, so while we were talking, she was already. Okay. It's three. Oh, we didn't know we did three. Okay, welcome everybody. This is the final afternoon session. In this session, we're going to shift our orientation. So that is why we're going to shift towards applications in evolution equations. I now hand over to our capable Professor Wits.
Thank you. This talk continues on from yesterday morning's talk. And if you remember, yesterday morning we used the model equation of the Laplacian. And where I'm actually going to start with today is a little bit of theory. We will soon get onto the applications, but this is a lot of the equations you look at variable coefficient. They're not Laplacian. So before we get into the time machine ones, take us just through the extension of what happens when you get into deal with variable coefficient equations and deal with the structure. And so previously we had the H1 norm and the H1 inner product, and that worked beautifully with the Laplacian. But in general, we're not going to be that much, even with second order equations. So your abstract problem is generated by a general form of dot on your Hilbert space H. And we want that to be continuous on that Hilbert space H. When we were dealing with the Laplacian, this was the H1 inner product here, and the Hilbert space with H1 and H10. This is an abstract Hilbert space, and we want it to be bounded. Indeed, so by bounded, we mean that the model acting on UV is less than equal to K times the H norm of U times H. And we want our forms to be linear in the first argument and conjugate linear in the second. Means Riesz representation. Our general problem now becomes a continuous statistical linear form. We have F in the dual space H, and we want to solve this equation here. A U V equals F on V all V in H. We want to get existence, uniqueness, and continuous dependence. So we have to work hard at this. And like this one, we can start in the same way. We have that map from V to A to V for a given U is a continuous conjugate linear function H. So we can apply the extent. No problem. We apply the inverse of the H Riesz map to that, and we get the element U, which is the inverse Riesz map onto the linear function of AU of dot. AU of dot, the linear functional. The Riesz method takes effect to the element generated in terms of the element. So we get immediately that alpha U, which is the Riesz method of U dot, P is equal to a functional AU applied. Yes, Riesz maps. Okay, it's reaching to show that this map alpha is linear in U. It's a problem. Dispute about that. Let's have a look here. We know that the absolute value of A and B is less than equal to K, norm of U, norm of P. So that means that if we replace P by alpha U, we get that the value of A U of P is equal to the inner product of alpha U of U. Step back, and we had that. So I'll put in here B equals alpha U. And we get that, which is less than or equal to K, norm of U, norm of alpha U. And all we have, that is the norm of alpha U squared. We can cancel out the norm of alpha U from that side, and it gives us the norm of alpha U system. So alpha is a bounded linear operator. So, where have we gone to? So our abstract problem of A U V equals F of V or V can be written in terms of alpha, and alpha U V is equal to the inverse resnap. Okay, in other words, alpha U is equal to the inverse resnap. Now, bottom line is you can't go any further without numbers. Because you can't say much about the invertibility of. And the standard condition is that the second linear form is to be equal to H group on H, which means that the absolute value of B is bounded below by C times some total constants. Now, what does that tell us? It's actually going to tell us, give us a whole lot of things. It's going to give us the injectivity of alpha. That's the first step. And it's also going to enable us to show that, in fact, alpha is subjective. And it's another nice. So, causability implies injective. So if alpha U is equal to 0, then it's like, so that certainly is not 0 is the value of U. But that is the absolute value of A U, which is bounded below by C normal. In other words, U is 0. So that's the first easy step. So coercivity immediately tells us that that map alpha is injected. So we have a candidate. We can, in fact, invert it, but we don't know how the range of it. We have to work for it. So let's show that the range of alpha is negative in H. Okay. So suppose that we have some element W to orthogonal to the range. Okay. So then we have that alpha W is 0. W is orthogonal to the range of alpha. But that is the absolute value of A, which by coercivity is bounded by C times the whole square of W. So again, W is 0. Okay, so now we have that the range of that map is dense in H. The last step of it's showing that the range is closed. Okay. This takes a little bit more. Okay, so we take a W that's an enclosure of the range. Okay. In actual fact, as we already know, the range is X. So nothing in the enclosure of the range is any element in H. Okay. Since W is in the enclosure of the range, there's a sequence U in H, so that alpha of U is to W. Okay. So that tells us alpha of U is a Cauchy sequence. Right? So if I look at what the difference is of the norms of U and L look like, it's multiplied by the norm of alpha U N minus alpha. Okay. We're working all this inequality backwards there. Okay. Let's just hold this inequality back there. And that is alpha of U minus UN. UN minus U. But that is just A of U N minus UN, which by commutativity is bounded by C of the norm of difference. Ha! Ha! We can cancel that term there with one of those. That tells us that the norm of alpha UN minus alpha C times the norm of UN minus UN. But the alphas of the UN, the sequence of alpha UN is a Cauchy sequence. So this term here is UN N and N tends to zero. It's zero. But that's and that goes to hence UN is a Cauchy sequence. We're in a Hilbert space, so the Cauchy sequence converges, let's call it some letter U. Okay. Good news, we already know that alpha is continuous. So, alpha of U tends to alpha of U, continuity, but we also know that alpha of U tends to W minus construction. So, W is equal to alpha of U, so W is the range is closed. The range is dense in H and it's closed. It has to be the whole of H. So it's adjective. So we have that alpha is bijective. That's inverse. Okay. The last thing is we have a solution theory. So we've now proved uniqueness and existence of solutions. So we know that alpha is, but we don't have the continuous alpha. So let's sort that out. Let's use the coercivity again, and we work all the inequality backwards. So we've got the norm of U times the norm of U is greater than or equal to the model of the product of the two, and we write there's something missing there. So that is alpha of alpha U in a product of alpha U, which can be written as A. So that is A of the inverse alpha inverse U of U, which is by commutativity bounded by below by C norm of alpha. It's the next U, norm of U is an upper bound for C times alpha to the minus 1. Where it's alpha to the minus 1. U is a norm set. Missing there is bounded above by 1 over C. That's the bound. So, we are in business. We can complete our proposals for the general form of these operators where they're not when we're dealing with things which will be on the Laplacian and the variable coefficient. So now this equation here, A u v equals f of b or v, and it's a solution, unique solution, and that solution is bounded by normal lines. That's plane, and it takes 4 lines, 5 lines, 6 lines. So we remember we rephrased alpha equals the inverse reason. Oh, well, we know that alpha is invertible, so we can inverse. The solution is unique, and the norm of that from our previous bound is equal to norm of mu is equal to norm. And the norm of minus 1 is bounded by 1 at the c argument, and inverse Riesz is a so that is 1 at the c f h2. Okay, so that concludes that development. So that takes what we did yesterday through to variable coefficient equations. If you solve variable coefficient equations, you instead of the Laplacian, you have to end up with 4a. Okay, so we've stepped up a factor. Now, we're also interested that we go into the world of time-dependent problems. Now, one of the ways of dealing with time-dependent problems is semi-groups. And in actual fact, semi-groups are a major problem to try and do all the mathematical foundations needed to make it work properly. Because hidden in there are tens of products all over the place, a whole lot of other structures where people wave their hands. So to actually clean up the mathematics there is a hard task to make it. So another approach is, well, set up our Hilbert space nicely at the beginning. So pack time into the Hilbert space as well. Then dealing with, so this is your, if you like, your non-time dependent particle space H, and that is inner product, it's called the zero inner product. H inner product. Nice. I did that. And then I switched it to 0. It gives some bad notation. Okay. And let's we set up this space. These independent phi's, they take phi maps from time through to set. Gradient. Okay, working with the mirror. Okay, and that is our state. So this is our H inner product. H prime, H norm squared, T, and we multiply that by e to the minus root of T. And we integrate that. Then the state H over 0 okay. This is my 0 with a bad.
How come time doesn't stop at 0? Why is time minus infinity?
We actually we can work on I. we were interested in a particular problem when we were doing this. But obviously you can restrict your time to positive x. I think at the end of the day, but we have here the time derivative, d0, and that was on the Hilbert space. Okay, and back. And this is that takes us from, we start off with the function is then it's this derivative, export, and we add it into here's the 0, 1, and continuously should have this should be 1, 0, 1 by second continuously differentiable function and by so and this is the extension, it's the extension of this to the next. So let's look at what happens. We can work out the adjoint of the and it looks like that. It's a computation, you can do the computations with respect to the end product. Yeah. And you'll get that this adjoint of d0 looks like minus d0 plus 2. So the real part of d0 is 1/2 d0 plus d0 adjoint, which is equal to 1. Okay, now if we take m as a bounded self-adjoint operator, time independent, h, then m commutes with d0, and commutes with multiplication. So we end up with the real part of d0 as being rho times d0. So if we take A as a self-adjoint operator, so A star equals minus A, and we work on the intersection of the domain of A with D0. By this, we need to explain what that means, because in actual fact, they're subsets of different spaces. So we find that this is an abuse of notation. But we need a shorthand. This is everything in the domain of D0, so that U of T is in the domain of T in our time. And this is density in H rho 0. As H is self-adjoint, we have the real part. So now we have the operator that we actually want to say. And that is D0 plus M1 plus A. And we'll talk a little bit about the operators. Here, M1, H is bounded, and we have that real part of the inner product, the rho 0 product U with this operator activity is equal to U rho and 0 U plus the real part. This is for U in X. If we make the assumption that rho and 0 is real part and 1 is bounded below, strictly away from 0, and our rho does this for each of the rows in 0 infinity, then closure of that continuous inverse bounded by C. And that leads us to the following structure of multiple systems with this continuous. And that is, if we obey all these assumptions, the problem resulting from the closure of the U, the unique solution in H equals 0, and the inverse map of that. And the application is Timoshenko B. So this is the Timoshenko B system. We've got this differential equation here, differential equation there, with these identification being set eta to be d0 phi, s to be d0 u, d1 to be k1 minus 1, d1 phi, b2 to be equal to k2 minus 1 over k capital 2 times d1 units. We do that and there. And in the new variables, the Timoshenko equation, this and that can be expressed as 0 plus n1 w equals n is vector 0, 0, w is v1 eta s 2, and m1 is kappa with a diagonal operator, multiplication operator. Dependent. M1 is this weird matrix here, and A is the sweet. Okay, we take out our space, which stays at L2 minus 1 minus 4, and we apply this very simple Dirichlet conditions. And solution. Next problem. Hamiltonian systems. Consider that we're actually interested in particular in the case of a one-dimensional Hamiltonian system. Cut up the pieces where, in our case, we're going to deal with H as being L2 on an interval, L2 directs L2 on an interval. So the one-dimensional Hamiltonian plus the one-dimensional. It actually operates in 2 dimensions. And we take the domain of A, the domain of C star, and the domain of B is 2, C X. We require C to be closed and A to be defined. And so, and we take over the non-empty. Okay, then A is a and we could replace it now continuous operator from the domain of HA to be HA1A to be the domains of A1 plus A2. Then each of those the Hilbert space with respect to Okay. And this now becomes unitary. And it's actually 0 to 30 to our base to the to 2. And we can work backwards. We have to do a lot of completion there, and that leads us to a chain of Wits. This gives us the unitary map. Now, we have a continuous against continuous operator. So our aim was to get to the continuous operator. You know, work on convergence, meaning convergence in one of the HQs. Usually one A is not. So this is an alternative framework for looking at Hamiltonian system. We had a, this is a, there's a reason why we did this. This is actually a recent piece of work with Ryan and and the cunning plan here is that in actual fact, external, it's well known that there are some thermodynamical systems, Hamiltonian systems, and some Hamiltonian systems. But in the framework we worked in there, you can show that that's always the case. All Hamiltonian systems, all Stern-Weaver operators are nothing more than Hamiltonians. Stern-Weaver operators. This is an especially Stern-Weaver operator, but one can always show that Stern-Weaver have a corresponding Hamiltonian system. And the cunning trick comes down to what's known as the Darwin-Crum transformation or the Darwin-Crum operator factorization. And that gives you the key to getting a correct Hamiltonian system. Okay, yeah, that's where that fits into life. And one last problem, dating back to many years, problem worked on over the many years is still a little bit. This is a very simple one, and we can make it more general. All sorts of other coefficients and that focus is now I took the simplest of the two shape and that's the piece that I want to do. Because one of the things we're looking at here is basis versus operator. So, in electrical engineering and many areas, you have this dynamic, takes on the form of an infinite function. It's poles at these points, these complex poles, or real poles like that. And this function f, we're restricting ourselves to the rational part, rational linear function, simple pole. It's target as f tends to infinity. You can deal with the other case. There's a second case of a linear function which goes to infinity. You can deal with it. You have to do some changes to the formulations. I'm dealing with this case because it's not that you can't deal with the other case, but you have to change your formulations. So what we do is, how do we get this into an eigenvalue problem? We want to get this into an operator eigenvalue. So these are the conditions on C's, non-real C's, and weight there. Okay. So how do we fix up this problem so we can deal with it? Well, if you look at this, we can rewrite. We start by setting yj to equal to bj lambda minus cj. That gives us this condition that cj minus lambda times bj y. And then you have one last condition, the sum of the put that into the matrix formulation, you get this very nice matrix formulation that you actually have that matrix condition. So your lambda number multiplication by the y j. So, and we have that condition, which you will actually at the end of the day. So we said that we can now set up our operator. So now we set up our space. We're going to work on L2 divergence on CM. This is going to be our operator. It's the differential, still legal of the operator. And this other part of the boundary condition. Is y function y, and then the set y the main condition, we force this condition, and there is a Hilbert space, and this is the domain space. It's the domain. And we now can work back again with the eigenvalue to this operator. And then it is indeed all these conditions, and it gives us that. But the problem is, there's a problem. That this device here, if we want a nice solution here, we would like to operate here. This is a basic defined, but it's not self-adjoint symmetric. So we have to custom build in the product. And custom build new in a product is this system. Now, it doesn't take a lot of calculation to see. Look at what's happening here. That need not be positive definite. And it's so it's the property that it's symmetric. It has a whole lot of the nice properties of an inner product, but it lacks definiteness. Fails the definiteness conditions. This, but it does meet the conditions to be contracts. So that is in a product type structure where you remove the positive definiteness condition, and the space in which failure happens is finite dimension. If it were infinite dimensional, you'd be able to contract. price. Okay. So if you start breaking up this inner product, you can see how many negative squares are. So you can work out the definite dimension of the negative square. So we end up with space levels like this, H1 direct 2. We have a second linear form, it's positive definite of H1, it's negative definite of H2. H2 is finite dimensional dimension. Okay. And we can actually work it out. So this H, this is called an indefinite inner product space. Now, unfortunately, there's a solution theory that belongs. So, with such an operator, we already know that compactness of the resolvent do that. So L is an operator, there's no it's H. In a product that itself adjoint with respect to that we have in a product. So that gives us the spectrum of our consistent discrete eigenvalues. The algebraic multiplicity of each eigenvalue is finite. There can be non-real eigenvalues, even though it's self-adjoint in this space, there can be non-real eigenvalues, but they're period conjugate. There are only finitely many non-real eigenvalues. There are only finitely many non-simple eigenvalues. The eigenvalues accumulate only at infinity. The eigenvalues associated with associating vectors, in other words, the Jordan chains, give rise to a complete system. And a complete system is orthogonal with respect to our distribution.
What's the point of introducing the covariance method?
Sorry?
What was the point of introducing the covariance
method? The original operator. This operator
historically, why do people start looking at this particular space? Because it's got so many characteristics. Well studied.
Yes, it's almost as good as a hundred. Self-adjoint operators on a country eigenspace are almost as good as self-adjoint operators on a country. There is, as I said, all your problems are finite dimension. In other words, the difference, you can have finitely many eigenvalues which don't obey the properties of a self-adjoint operator. So it's a very contained problem. And as far as I know, the major area that I'm using is exactly this studying such. The origin, I'm not entirely. There was quite a lot of work done on just general spectral theory in country eigenspace. It was the Russians who started in the 1950s and 60s. So when people started looking at generalizing Hilbert spaces, this was one of the generalizations. But it's actually a very useful generalization. Generalization where you have a higher degree of indefinite you get what's called a grind space. But there, it breaks the structure significantly. You can have a self-adjoint operator in a grind space, and it doesn't necessarily result in. Maybe you're better off studying the original operator in the grind space. At least that's my opinion. That's possibly a biased feeling, but certainly for the patriarchal space, the structure is sufficiently nice that it's worthwhile. You can read off a whole lot of results. And that's where I'd like to end. Is that right? Okay. I thought that was the interesting part. But there are many more things you can do. So this was these are an eclectic assortment of some of the problems. There are also other things along these lines we can do. You can extend your life beyond linear. You can go into the world where you have operators that are homogeneous but not additive. So there's, I don't know if you've heard of the P plus. The P plus gives rise to an operator that is looks very much like things like symmetrical operators and some of the other operators look like. But the operators are not linear. It is homogeneous, real homogeneous, but it's not additive. And that gives rise to a whole lot of interest. And again, you can build working in Hilbert space. And you can build spectral theory, you can build a lot of structure that works for such. You have to work quite hard. But you can have eigenvalue problems for these nonlinear. If you have enough structure to look at Jordan chains, amazing. And they come from physics problems. It's not as though they are from weird and obscure. These things come up in electrical engineering.
Yes.
And the half linear in fluid dynamics and various areas of weird fluids. So yes, they have their roots in genuine application.
Some dynamic boundary problems in heat equation, elementary heat equation, dynamic boundary in the form of mix. So one end is liquid, the other end is dynamic.
Yeah.
In that can be written implicit evolution equation, like d by dt of bu. So instead of a, by t u, you have a juxtaposition bu. And this involves two distinct state spaces. B is mapping from its y into x, and y is a significant part. Y is a total part, x is a significant part. So it's an extended form of the abstract Cauchy problem, which has a setting of one state space. So we now move into two state spaces because you need simultaneous consideration, because you're not taking the boundary as a body in its own right.
Yeah.
So that's why you end up looking at two spaces. So that system can be written as an implicit Cauchy problem. It's just a time derivative of BU plus AU equals, let's say, everything is 0. Then of course you then have your initial condition, where you just pre-assign certain pre-assign these two coupled fields. Does that, if I go to your slide where you have the D0, M0 plus M1 plus M closure, does the B become the M node? And if I try to fit it into the scheme, does the B become the M node? And now your A here is symmetric. Let's say the A is A M1.
Not sure. But we can send you some of the work we've done in that setting on dynamic boundary conditions. I haven't looked at the problem you're talking about. But, we have looked at dynamic boundary conditions in the setting. I will send it to you.
You will give me if cost your extended how many years did you take to operate this?
This, the differential equations that we've been working on about 1990. I've been in differential operators for many years.
Oh,
About 25. No, tomorrow I'm looking at ergodic theory and when you get to statistics. Restart places I'm going to get. But there are these full functional notes. And well, years ago, I went to a talk by Wolfgang Arendt. Netherlands, I think, and he looked at solution theory to Laplacian problems. That's nonlinear problems. Engineers non-additive differential operator. And he looked at them via the vector lattice. So there is you can connect the two theories, the two areas. He talked about that many years ago. 10 or 20 years.
Can you give an overview of that pathway? The A was non-symmetric, original Hilbert space, then you set up this non-Hilbert space. What was the, can you give us a rough intuition of how the construction worked, specified, operated?
Yeah.
Yes.
Okay, so the first thing, there's a couple of problems. The first thing is you look at, you want to, the F here is nonlinear. you have to pose this in a way that you can access it as a linear matrix problem. It's linear in number. So how do you go about that? You go about that by, if you have the solution to that matrix, if you have an eigenvalue to that matrix, you find when you eliminate the y j's, you find that you exactly satisfy that condition with f as given it. And that's the interesting thing with the never-linear function. Technically, you could actually do this for an infinite pole never-linear function. But it becomes, it's quite difficult as it is, technically difficult to handle this. So the first thing is you linearize that condition name by this setup here. So you take this piece here onto your operator. Okay, and you take Cm onto your space. So now you know that if you have an eigenvalue of L on this domain, it is an original problem, and you can recover what your function is by elimination of the y. So it's a faithful representation. The problem is in the fact that now, so that's what it will look like if you have the problem comes to what is your eigen, what's your spectrum theory? Because your operator is not self-adjoint. This is your Hilbert space. That's a Hilbert space. Under the usual integral, it's densely defined. There's no problem with density specification. But it is not self-adjoint or symmetric. So, yes, you could go and try and deal with it as just working with Hilbert space theory or non-self. Or you can say, well, what in a product, how can you change your space to make your problem a nicer problem? Just as we've done in yesterday's talk. How do you tailor-make your spaces? How do you tailor-make your spaces to deal with your problem? How do you reformulate it so it's easy problem? And the answer is, well, redefine your inner. Keep the space the same and redefine it. And when we actually grind through it, the inner product that will make it operate alphametrically is this. So it's a direct computation. The problem is that, okay, if there are no complex eigenvalues, no complex weights in go back here. So if this piece of whatever negative function is void, so it's a real negative function, this piece here disappears and now then you only get that piece, and if the bk is positive, then indeed this term disappears, and this is a positive definite term. So it isn't in a product. So you've now taken your space and you have new inner product. And this is now a genuine inner product. In that case, it's not an indefinite weighting. So it has all the normal. If that term is missing and the bk is all positive, well, it's not an inner product. It's a new inner product. predictive handle or eigenvalue. So in that case, your space H2 is just a zero space, and everything, you have a full space and you have stagnant space. So you don't have to deal with the case in general like if you have a very nice one, those conditions are met, then it's the limit space. Then you've taken a nonlinear problem, linearized it, solved it in a suitable space. You can do this with PDs as well. There's a guy who postdoc as well. He did a very some elliptic PD just for linear type boundary. Didn't have general. He had, this was just lambda. So it's something like a Wits boundary condition. So you have dynamic boundary conditions, but it's either lambda on that side or lambda on that side. It's still intrinsically linear, but you just tack on one extra boundary space. And that is an easy extension from elliptic theory through to the one where you have just linear dependence, lambda. So that has been done, but technically you can do it for functions of finite boundary space. Yes.
Thank you, Prof. I wanted to inquire if the same idea that we use here in proving uniqueness and existence of solution can be extrapolated to fractional PTs.
I've never tried. That's quite likely.
Prof, I also wanted to ask.
It's all about, can you find a suitable space? And this the story of fractional PDEs is building the right space that they work with. So if you have a suitable space, then you can do it.
Even if it's fractional.
Sorry?
Even if it's fractional.
Exactly. So long as you have a linear structure on it and you can show it's a Hilbert space, the fact that your differential operator is a fractional differential operator doesn't really matter. So long as you can get the correct structures, you're fine. So I know there are people who work on that sort of stuff, but I haven't been tracking it. Not.
Apart from the idea of taking PTE like Laplace, we have the Laplacian of y plus y equals some function. Then we transform it to an abstract problem.
That's right.
And then the existence or studying under the abstract consideration. Now, is there a possibility to study the existence without taking that path? Is there maybe an easier way looking at the existence of the PT without that transformation?
Well, there are many different ways to study the existence of PDEs, of solutions to PDEs. This is one of the ways. There are people like Elmer Rossingen that showed existence theory for PDEs using order structures. But there are many different ways that people have approached existence theory. So
Okay, everybody, I think this is a good place to end. Let's please give. This closes our afternoon session. We hope Prof Watson gets enough rest for the last session tomorrow. But we are always grateful for his efforts in sharing this really deep knowledge, which not even AI can give us. See you tomorrow. Thank you.
It's today.
Wait, I think it is.